Hi, I'm Ken Miller.
And I'm David Erdos.
And welcome to the Erdos Miller New Technology Podcast, where we spend our non-productive time talking about everything drilling tech. David, speaking of non-productive time, I'm actually broadcasting from beautifully sunny and windy Midland, Texas today, with all the awesome drilling rigs around me. So our guests today are two great guys from Superior QC, Mr. Chad Hanak, who's the president of Superior QC, and Ryan Kirby, who's the VP of operations for Superior QC. Welcome, guys.
Thank you.
Thank you.
And so, David, what will our topic be today?
So we're going to be talking about survey corrections. We'll start off with a little bit of history of what survey corrections are, why we need them, maybe a little history on Superior QC from Chad, and a little bit of the entrepreneurial story. And then we'll get into some of the more details on the technical side.
I mean, Dave, let me just stop you right there. I don't think we need to do this podcast. I mean, our surveys don't need corrections.
That's right. We provide perfect measurements with no errors.
Yeah. So, Chad or Ryan, just to start us off. So what is a survey correction? Why do we need to do that?
Yeah, so it's funny. Ryan and I were talking about that earlier today. I think we came up with a pretty simple analogy to explain why survey corrections are important. So you can think of a scope for a rifle, right? And you can machine that scope to the highest degree of precision, test it over and over, make sure when you make an adjustment, it stays no matter how much you knock it around. But when you take that scope out of the box and put it on the rifle, you're not going to hit the target the first time, right? You've got to sight that scope in. You have to go through that process of in-field calibration of the overall system. It's no different when you take the greatest MWD sensor probe in the world, put it in a pressure barrel, put it in non-mag, screw it into a BHA, and put it down hole where you're telemetering the data up through mud with a system that has a lot of the setup via manual human input. You don't expect it to work right out of the box. And it's not that there's anything specifically at issue with the sensor, it's a system issue.
Yeah, does that analogy, can you extend that a bit further, right? Because with a rifle, you have to compensate for wind and distance and other things like that. Does that analogy work further?
Yeah, so it does. Oh, go ahead, Ryan.
Well, I was going to say that actually came up when Chad and I were discussing it. When you think about windage and elevation, you're talking about more advanced types of survey correction where you're pulling in additional data from the rig stream or the data lake that's available that really the history of survey correction hasn't done up until this point like we're doing today.
You said data lake, which is one of my favorite words and way too nerdy to go into here. But I mean, you said not working out of the box, right? So I can take, you playing with your analogy, we can take a rifle and we can, aim it at a really big target really far away out of the box, and we're probably going to hit somewhere on that target, right? But the reality is we want to hit the bullseye, right? And to do that, you got to have a very accurate rifle, a very accurate scope. And on top of that, you have to make all sorts of corrections and adjustments and all that kind of stuff, just nail where you want to go. And that's where something like survey corrections comes in when we're talking about drilling. Yeah.
And to, take it a little bit further, you mount the scope onto the rifle. The biggest thing you're worried with right away are mechanical misalignments, things that are constant. And so that's kind of your standard survey corrections, your multi-station analysis, fitter, address those kind of systematic fixed errors. But then, talking about windage, talking about drop due to gravity, we can make that analogy to a more advanced kind of navigation algorithm where, we don't measure our position in 3D space. We measure angles at discrete points in the wellbore about 95 feet apart. And then we make assumptions about how the wellbore evolves between those points, which are sometimes very dubious assumptions. So you're going to have drop tendencies in rotation. You're going to have walk tendencies in rotation. And you really, to get an accurate placement inside your reservoir, you want to estimate what those are and account for them, because you don't have a smooth minimum curvature arc between your surveys most of the time. And so that's kind of the exact same thing. And the more data you get, the more feedback you get from sensors, like incorporating continuous sync, that sort of thing, the better those estimates are going to be.
Yep. No, that's solid. I mean, because you make a good point, right? A short color correction can take care of one of our most common things to talk about, which is Z-axis magnetic interference, right? And that's not changing much from station to station, and you can take care of it. But that's just yes, it's an error source, but it's there's so much more that goes into it than just that. And No, I was also going to say that, like, most of the world has moved on, like anywhere possible, like ships, airplanes, whatever, has moved on from, magnetic based navigation, or even, away from, like, what we're stuck with, which is like dead reckoning navigation, right? And so you mentioned earlier, kind of talking about angles and discrete points. I mean, we're still stuck doing this very, very basic type of navigation under the ground, similar to the way that ships used to work hundreds of years ago, because we can't get a radio signal through the dirt to basically, use a GPS underground. And so we need all the help we can get because, more accurate, better location within the formation, more oil, right? More resource, whatever you're going for.
Yeah. Well, actually, ships had a leg up on us because they could use a sextant with a chronometer and actually get a rough position fix, an absolute position fix. Like you said, we're just dead reckoning underground. So it's more difficult than that.
We no GPS. You can't use a gyro because we rotate and vibrate too much. And by the way, you can't see the stars either. So best of luck figuring out where you are. So when did this whole thing start? Like, as an industry, how long have we been doing survey corrections?
Well, I'll take a stab at that. So field acceptance criteria is something that the industry has been using for about 40 years. And that's really just a gross error detection. Is the survey that I just took good or bad based on a set of qualifiers, which is your gravity field, your magnetic field, and your dip angle, and some allowable deviation from the reference field value that you expect. So for about 40 years, I've been using that. About 30 years ago, roughly about the same time that the ISC WSA was formed, single station correction was very popular and became more prevalent. It's still used today, probably too much. And then multi-station analysis was born about 20 years ago. And then here we are, FITR, the fourth gen is now, 5 years old, Chad. So it's been an evolutionary process, but each one of those represents a very fundamentally different mathematical framework and an approach to that problem to generate a solution.
And so, I mean, field acceptance criteria is basically as old as NAVD, right? So, like, as long as we've been taking surveys, we've at least been either accepting or rejecting them based upon some inference of their quality, right? Like, maybe we weren't, like, trying to back errors out of them, right? But just at least, only including the ones that were good and retaking ones that were bad, right?
No, I was gonna say, yeah, survey by survey, you're estimating that drill string interference component, and you're just resolving that error term one survey at a time, multi-station, because what you had mentioned earlier is that for a given run in the same BHA, your drill string interference shouldn't change too much during that run, so that becomes more of a systematic error. Then you can start to look at a handful of other error terms. And that's how multi-station analysis or multi-station correction was born. And that we can start to observe from the measurements that we're getting from downhole, different kinds of error terms and their impact on our position or our understanding in the position of the wellbore.
Mm-hmm. Okay, that's awesome.
I was going to say too, one of the reasons to move, the main reason to move on from single station correction is because people would do it over the course of wellbore, and they'd see their estimate of axial magnetic interference vary, and they would say, well, intuitively, that doesn't make a lot of sense, right?
Yeah.
So that you go to multi-station where you can nail it down and force it to be the same across multiple surveys. But then another thing we saw, which is kind of devil's in the details type of thing, is a lot of different error sources can look like one another, but they don't put the well in the same place. So we've seen, had been called in and had to do an analysis and recorrect some data before, several occasions where that happens. And a good example is, so you're going horizontal east-west, axial magnetic interference, potentially a large amount of it, is going to affect your B total reading one way, and it's going to affect your dip reading one way. But other error sources can also affect it in that same combination. For instance, you can have a cross-axis magnetic scale factor error or a B total, reference field error in your reference model, in addition to, say, a twist between your accels and mags east-west, and that can look the exact same. And if you don't choose the correct error source to solve for, you can put the well in the incorrect place by hundreds of feet. And we've seen 500-600 feet errors before because of that.
Well, there's some scary questions I can think of to ask, which is like, one, I mean, how many error sources are there? And I'm kind of terrified for you to enumerate them. And then, and then the other question is like, how often were you guys? So, I mean, we're talking about like a fourth gen survey tech, correction technology, or like we've been at it for 40 years. We're on the fourth major iteration of the technology now. I mean, the second and third gen technologies, I mean, what percentage of the time were those maybe backfiring on us and actually where we would have been better off and closer to the target with, just doing FAC or just some basic surveys?
That's a great question, Ken. That's a loaded question too.
It's a loaded question. Okay, I didn't mean to ask a loaded question. Sorry.
No, it's a challenge that the industry is going to have to deal with at some point. I mean, the fields that we're drilling in now are highly congested. There's a lot of well bores. We're doing a lot of infill drilling, well crossings. And the reality is that most of these operators are trying to mitigate known risks, but there are a lot of unknown risks that they can't address. And that is improperly placed wells due to these factors. And we have to deal with that all the time. I mean, we were doing one this morning. We have a multiple well crossing plan for a long horizontal section that's coming up. And it's very challenging to go back, 20, 30 years ago and try to process data that doesn't exist anymore because someone forgot to save it somewhere, or it's in somebody's CD in a closet, which we're not even using CDs anymore, but that's how they used to store data, right? So it's a challenge for sure. And opening Pandora's box and looking at old wells is something that most people really don't want to do, but it might be necessary in some cases.
I was gonna say, just to get like an intuitive idea of like how these errors build up, like what kind of ellipse of uncertainty are you looking at with zero corrections versus like the most advanced corrections we're capable of today?
So
just ballpark.
I would say for the east-west direction, this one sticks in my head. Probably looking at 3 standard deviations, left, right, you're looking about plus or minus 300 feet, call it. And with corrections, you could probably get it down to, depending on your reference field, magnetic reference model, between 100 to 100, plus or minus 100 to 150 feet. If you have
3 times more accurate.
Yes. But then with our 5th gen software, we can basically combine different error sources. So, overlapping MWD and gyro, that sort of thing, and attack different error sources that may not be observable with just a single MWD run and actually reduce that further.
Dave, my joke was going to be, I'm not sure that all of the data stored in the Texas Railroad Commission surveys are synonymous with high quality,
I'll say I've got a number for you, just a couple of numbers just to talk about how prevalent these spacing errors can be. And this is just versus not doing anything. Great. So we have we've had an operator do a few production studies on spacing errors versus production. We see in the north-south direction, if you're drilling within 15 degrees of north-south, 10 to 11% of wells are going to have 100 to 150 feet of spacing error. I think it's about 5% will have over 200 feet, and like 1.5% will have over 300 feet of spacing error. Now, when we were doing the production study, obviously the operator was doing the production study, they shared it with us. They were doing, just a couple of years ago, 330 foot spacing, and they had about 120 feet of spacing error between 2 wells, and they happened to converge rather than diverge. And they had a 3rd well on the pad they could look at as kind of a control. Well, they estimated that across the pad, they lost about 10% of the production they expected from those 3 wells. And so we can take that, we can adjust it for different spacings and calculate with those percentages I mentioned, how much production you might be losing by just, again, taking that scope directly out of the box and running with it and not trying to actually refine your knowledge of the system errors.
Yeah, I mean, that probably adds up to millions of dollars over the life of the well, I imagine.
Yeah.
No, that makes perfect sense. Well, and I was going to say, I mean, we're also, as an industry, the requirements just continue to go up, right? Like, I mean, when NWE started, a lot of the wells were still mostly vertical and, into conventionals, right? And we were drilling horizontal wells, and now we have pad stuff. And then, these interleaved infill wells where we go back and forth, and the spacing requirements are tighter and tighter. And so, I mean, not only is this enabling a lot more stuff, but it's also like there's higher demand on, groups like yours to come out with even better technology to help us navigate into the future as the requirements keep going up.
Yeah, absolutely. I mean, that's where the fun is too. So we appreciate that challenge.
It is fun, right? Like it's a very nerdy type of fun, but it's a very awesome thing to be able to like look at these things in this kind of detail and try and solve them, right? So Chad, I mean, tell us a bit about your entrepreneurial journey. Did you guys start Spirit QC just to bring the fitter stuff to market, or how did you get started?
So I remember it was back when I was at one of the larger service companies. We'd go into meetings. I was in the research group. We'd go into meetings and they try to decide which projects they were going to fund and which they weren't. And it just struck me at the time that unless something was going to return 50, 100 million annually, it wasn't worth the time to fund. And I was like, man, I'd be happy with a project that returned 5 million annually, right? Or 10 million annually. So I kept that in the back of my head. I ended up going on to another company for a while, thinking a bit more about, what might be viable products, options. And eventually I split off and started Superior QC, and Fitter wasn't actually the product yet. It was just a more automated, more informative multi-station analysis. It didn't fix the issues with multi-station analysis. It just told you where they might arise. Mm-hmm. So it told you when you were in a potentially precarious situation. It took a whole other year to figure out how to actually fix them reliably with Fitter.
Okay. And so some of your background is in aerospace and space. Was a lot of that kind of knowledge or experience applicable, or how did that transfer?
Oh, absolutely. And in a couple different ways. So I've done a lot when I was at NASA for the bulk of a decade between being a co-op and working there professionally. A lot of navigation work, so mm-hmm. a lot of space navigation work, and the mathematical backbones are very similar. It's just the measurement types tend to change, and guidance work too. So had a lot of background there. And then the other aspect of it was just experience designing flight software. Because I'll tell you, the first time, like the amount of computation that happens in Fitter is geometrically higher than the amount that happens in a typical MSA algorithm, multi-station analysis algorithm. And so the first time I ran Fitter on a well, when I proved to myself it worked, it took 3 hours to run the computations. I said, okay, well, that's great. You figured something out mathematically, but you don't have a viable product yet. But because, when you write flight software, you have to write efficient code. I mean, you're literally slotting code into sub bins of a 5 millisecond cycle slot, and it has to execute reliably in that period of time. We were able to get it down to where Fitter now cycles in about 2 seconds.
Oh, wow. It's a big improvement from 3 hours.
Yes.
Okay. And so a lot of the same techniques and, obviously navigation, and you said the math is the same. I assume the error sources are quite different, or a lot of similar ones as well?
There are a lot of similar ones. I mean, space, you've got your cells, you've got your gyros, you're going to integrate the rates that come out of them basically over time. And then you're going to re-anchor with external measurements like star tracker measurements, GPS, things like that. Here, we're actually sampling angles relative to the field, or, the tri-axis vector of the field relative to your frame, your orientation. So that's a little bit different. What we've done with our 5th gen product is we actually have a model of motion, an equation of motion model in there as well. So it's gone back to a little bit more standardized format, and that's really allowed us to do a lot more with bringing other types of measurements in and improving the solution.
So, I mean, one thing that we haven't talked about that's a bit different, right, is one of the things, I guess, that kind of came out, I guess, with the 4th gen technology was actually the automation as well, right? And this, a lot of the stuff, the FACs, the single multi-station analysis used to be quite manual.
Yeah, Brian, you want to grab that one? He's done a lot of the pushing on us on the development side to make a lot of that more automated.
Totally.
I mean, I've been in this industry now for going into my 17th or 18th year. It's hard to remember. I don't sleep much. But what I can tell you is that with the digitization of our industry, and the first rig I was ever on was a Kelly rig. Now we have, super spec rigs that can make a stand up while they drill one down. So the push for automation, the push for tapping into those digital data streams that are more readily available today was paramount for us when we're setting out to design an improved version of what we can already do. And our development team is great. I mean, all the people that work here at Superior QC are very smart, very brilliant people, a lot of outside the box thinkers, but we're constantly challenging ourselves and getting feedback from our customers, the operator group, on what are they really trying to do? What are the problems they're really wanting to solve? And with as much data as that we're generating from the rig side and trying to run that into a survey management process and algorithm, automation was the only way to go. And so we have spent a lot of time setting that foundation, building digital APIs, building framework for exchanging data via protocol. And I think that's really the path that the future is going to follow. It's just going to be more of that.
That's a solid point, right? Like, the first, we've got our two softwares talking right now, right? So the NWD surface system is sending data to you guys automatically for processing. And I was thinking the other day, like, at this point, a rig literally drills better with an internet connection, right? Because you can have all the remote centers chiming in and providing the additional monitoring. You can be running, software on the back end, consuming the data and providing guidance, feedback, better positioning. That's just not practical to run on site. And so internet connected rigs at this point literally have a distinct advantage over guys who are still trying to do it the old school way, right? But I mean, while we got a lot of the human error out of it and a lot of the just automation, what I'd love to say about automation is that, our goal should not be to remove people, but it should be to allow the people that are doing the job to spend 100% of their time doing creative thinking and problem solving versus just, doing routine tasks, right? But very quickly, we're going to be overwhelming like anything in exchanging more information than a human could ever practically intervene and send for us, right? And the automation just becomes absolutely required to keep pushing the boundaries of what's possible.
It's paramount. It's absolutely paramount. I mean, I think you hit one of the key points, and the design idea is not to replace what the human can do, but augment it in a way that machines can harness that information much quicker, much more accurately, much more repeatable, and provide that individual with better decision-making capability in real time, near time, all the time. That is the goal.
Absolutely. So let's talk about the future now. So we're on, I guess, 4th gen was for you guys was fitter, right? And I guess you're calling the hi-fi nav stuff the 5th generation. I just want to make sure I'm on the same page with the generations, right?
Yeah,
Yep, you got it.
Okay, but so we're 40 years into this, and the 5th generation's come out now. Like hi-fi nav is commercial and it's running for you guys, and that's available for operators to come and enjoy, right? That's today's technology now. Even though it's the latest and greatest, it's not the technology of 5 or 10 years from now, right? So what can we expect within the next 10 years? Like what are the problems you guys are going to go and solve? What's the advantages and how much more accurate can we get and keep evolving these technologies for the next 10 years?
Well, I can tell you what we're field testing right now, and we've actually got a lot of successful field tests under our belt. Pretty good looking data is our guidance algorithm, right? So we've got that out there. It's built to be integrated with hi-fi nav, and that offers certain advantages. And one of the things is, we're able to get, especially as much data as we consume, especially when we can consume things like continuous sync, we're able to get really, really good estimates of, again, rotary tendencies. How are you dropping, over a couple stands or whatever when rotating? What are you doing walkwise? Did you just get push? We're able to get very good data, very accurate results from that, motor yield, all that stuff, and drill more efficiently. But it's because we can tune the two to work well together, because they're not, two completely separate products that were, brought together and bolted on. And we're seeing extremely good results. I mean, one of the things I was a little bit surprised with, we were testing with a lot of directional drillers who are experienced, good directional drillers. And I figured we'd just be a little bit more efficient placing slides, and we are, but we're also a lot more efficient at staying in zone, which surprised me. How, lower than I thought percentage that DDs are staying in zone, and I understand, with the target changes and everything, that could be a bit of a challenge at times. But so I was very pleased with that.
And so that's really awesome. Congratulations. And so it sounds like the 5th generation technology is giving you guys a really good platform to go out and tackle this automated directional drilling or drilling, performance guidance kind of problem, right?
Yeah, absolutely. We were tasked with doing something like that early on, and I was always like, I need a real navigation platform to do that. I need output from a real navigation platform, not this.
To do it first, right? Yeah, that I can see that. That makes a lot of sense.
I was just going to say, when you say guidance, like, can you describe what that looks like to the driller as far as like guiding the bit?
So it's in my world, we have sensors that take measurements about the real world. We have navigation, which fills in the pieces. So your sensors measure inclination and azimuth periodically in the wellbore at certain measured depths. Navigation fills in the pictures. Where am I in 3D space? What are my rotational tendencies? What am I getting out of my motor? What's my yield? Various questions like that. And then guidance, and so it tells you where you are, how far away you are from plan, what do your equations of motion look like going forward. Guidance says, what do I do with that to stay on plan, or to meet my objectives of being within plan. So how far can I rotate before I need to slide? What slide do I need to do? I want to do all that efficiently. I want to do it in an optimized fashion. So you have your guidance laws that do that. And then the control that's the hardware that actually executes the desired maneuvers, if you will.
Which in this case is still the human driller.
Yes, but there are a lot of automated slide algorithms coming online, or you could actually use rotary steerables too, is kind of that automation piece, if you can do the downlinks automatically.
Nice. Yeah, I'm really excited to see like what comes together between all the different technology stacks and providers over the next 10 years. Because Ryan, you said you've been here for 18 years. I've been in oil and gas for about 13 years. And I also started with Kelly rigs, and I guess I kind of started at the end of Kelly rigs, and seeing that, and just how far we've come in 10 years is crazy. I can't even imagine another 10 years of continuous development on all these different fronts.
Yeah, I'm excited about all the extra hair I'm going to lose staying up late at night and troubleshooting the uncharted waters that we're going to have to navigate. Right? It's been fun.
Come on, Ryan. It's not all troubleshooting.
No, it's not. It's but it's a different kind of troubleshooting now, Ken. I mean, you guys are exposed to that. Yep. You're developing technology that's kind of pushing the envelope and pushing these boundaries forward as well. We're having to respond to different types of challenges. It's not so much, hey, your product isn't working or something's not working. It's more. We want to do more with what's available, and we want to do it faster. We want to do it, again, more automated, more control, because technology is allowing us to drill deeper and farther every single year, and it's not going to slow down. It's just this is going to keep growing and changing, and I'm excited to see what the next decade looks like.
I'm really excited too, but you left out the best part. It's better, faster, with more performance for less money.
Everybody's favorite.
All right, guys. Well, this has been fantastic. Is there anything else you'd like to discuss with the listeners before we wrap up?
I'm good.
All right. Well, thank you, Chad and Ryan. I think that's all the time we had for today. For any new listeners, please be sure to check us out on iTunes and Spotify and YouTube. Thank you.
Thanks, David.
Thanks for joining us, guys. This was a lot of fun.
Thanks, David.
Thank you, sir.